Okay, recording is rolling. Today is Wednesday, May 4th, and we're working on this stats packet that we started yesterday. Okay. All right. So I know a couple of guys were not here yesterday. So if you want to see in detail what we did, then there's a video on Google Classroom. But I'm going to recap it real fast. I mean, probably everybody needs to recap anyway, because there's some new concepts going on. Right, we're eventually headed into quantum mechanics, but before we get to quantum, I want to introduce that, like segue into that with statistics. Give you guys a crash course on stats, because I think it's good to have a statistical framework to help to understand quantum mechanics. So you guys see that there's three populations here, right? There's dogs, people, and trees. I see dogs, people, and trees, right? And I gave heights for each of them. Now we're going to make a little bit of a crazy assumption here. We're going to assume that these heights, you've got 5 heights here, 5 heights here, 5 heights here, are each representative of a larger population that is what's called normally distributed. Right, you guys see 2 graphs here? Okay, so if you haven't labeled these already, label them dogs on the left, people in the middle, and trees on the right. And here's how you know that they're in that order. Because you guys see increasing height to the right? Okay, so the trees are the tallest. If you look at these sets of 5 population, these 5, these 5, these 5, the trees are the tallest. That's going to put them furthest to the right. The people are in the middle, like the Goldilocks height, and the dogs are short compared to everything else. So the dogs are furthest to the left. Right? Now that's the only difference of these curves, right? Left, middle, and right, dogs, people, and trees. Another thing you'll see is that, well, the dogs are all kind of spread out, and the trees are all kind of bunched together. That's related to something called standard deviation. Okay? Like what's the variability in the heights? The dogs and people, maybe it's really easy to conceptualize, right? So people, all kind of the same height, about 5, 6 feet tall. But dogs, you get crazy different sizes. You get little tiny chihuahuas, you get Great Danes, you get medium-sized dogs. So does it make sense that they'd be like more spread out? Now, as a consequence of being more spread out, see, like the area under each curve represents 100%, like 1. So if it's like more spread out, it's consequently going to be like stuck down a little bit shorter. That's the only reason the dog's graph is like kind of short, right? The fact that the dogs go short is makes them push further to the left. Right. Then the trees. Now, if you look at the trees, I gave the tree heights like almost all the same height. Maybe some crazy selection bias, like down at the local hardware store, we're going to choose all Christmas trees and move on. They'll all be about the same height. That's why there's almost no variability. See how they're all like bunched together like the same height tree, right? That's why it's a little skinny curve. Okay. Now, 2 numbers we're going to calculate for each one of these: mean and standard deviation. Okay. So you guys have probably known how to get the mean probably since elementary school, right? Just add them all up and divide by 5 because there are 5 of them, right? But what about standard deviation? Now you could go solve this long way, and we did this for one of these yesterday. Okay, so mean, add them all up and divide by 5 because there's 5 in the group. And standard deviation is this whole process. Remember, standard deviation tells you something about the spread of the data. Specifically, it's this. Do you guys see where the curve stops going concave down, starts going concave up? Like if there's an upside down ball here and a right side up ball here. The point where it switches is called the inflection point, and the distance between the mean and that inflection point is exactly 1 standard deviation. Okay. Right, so then I told you guys how to do this on the calculator screen. Okay, so here's where we're picking up from yesterday. So everything I said so far is just a recap from yesterday. All right, let's do this. Right, do you guys have this model calculator? Right, or if you're in stats, you know how to do this with the graphing, that's okay too. But I'm going to show you guys on this one. So everybody has this model, right? And if you don't, I see a couple of spares down here. Okay, you guys got this model? Ready to go? All right, let's start by doing this. Do second exit stat. You guys see second exit stat? Right? There's a button that says stat var, but above it says exit stat. So second exit stat, hit yes, that clears out whatever data was there. Okay. Great, guys good so far? Yep. Cleared up. All right, then hit second stat. There's a button that says data, but above it says stat. You guys hit second stat? Yep. And on your screen says 1 variable. Yep. Hit yes. All right, guys good so far? There's a little word that popped up here that says stat. Okay. Now hit data. You guys see data? X1 equals. Right. So if you're starting from scratch, I'll do the dogs real fast. Right. Type in my first dog, 85 centimeters. Scroll down. There's only one of those guys. If there's like 1,000 of them, you said there were 22 dogs, but just got 1. So frequency 1. Scroll down again. X2, 87. Okay. Scroll down frequency 1. Scroll down. X3 was 98. Scroll down. X4, 112. Scroll down. and the fifth dog was 123 centimeters. Okay, now I've got all my data entered. Now I'm gonna hit a button that says stat var. Hit stat var, and it does the calculation. In this 5, yep, there were definitely 5 dogs. Scroll to the right, X bar, that's your average. Hey, 101 centimeters. Okay, so I got that. Okay. Scroll to the right again. You see S sub X. That's your standard deviation. Ah, that's like this variability right here. So, well, except it's for dogs, but same idea. So 16.3 centimeters. Okay. Right. Guys got it? And everybody's numbers are different, but it shouldn't be crazy different than that. You might say 14, might say 17, somewhere in there, right? All right, you guys good? All right, now I'm going to clear up my data. Second exit stat, yes. Second stat, 1 variable. Okay. All right, now I'm ready for people. You guys ready for 5 people? Oh yeah, go ahead.
What's the standard deviation? Is it SX or AX?
Yeah, do the S. Yeah, do S sub X. You know what? Since you brought that up, here, there's yeah, kind of sorry about this, but there's different characters that are used to represent the same idea, sort of. I'm kind of glossing over a little bit, but you see this character for standard deviation, it's Greek letter sigma, and you'll also see an S. If you can choose between the two on your calculator screen, go ahead and choose the S, okay, for standard deviation. Okay. Okay. All right. So 5 people. All right. You guys hit data. You guys got X1. So my first person, 163 centimeters. Scroll down, scroll down. 169, scroll down, scroll down. 175, scroll down, scroll down. 181, scroll down, scroll down. And X5, 182. Right. Do you guys have your 5 people in your calculator? Right? Right, everybody good? All right, then hit stat var. In the spot, yep, we got 5 people. Scroll to the right, X bar. Okay, here's my average. Okay, so I'm looking at this many centimeters average height. And just double check, is that number kind of in the middle of those 5 numbers? Yeah, that's kind of in the middle. So I can believe that's the average. Okay, scroll to the right one more, S sub X. Standard deviation, I'm looking at this number right here. Standard deviation. Okay, remember that's kind of like a plus or minus factor. Okay. Actually, I'll tell you, so where this is going by tomorrow, is that if you do 174 centimeters plus or minus 8 centimeters, think of this like a plus or minus, that should account for about 68% of all people. Like 68% of people should be within 8 centimeters of that mean right there. Yeah. If all these numbers are representative of normal distribution, blah, blah, blah. Okay. Okay. So you should have these boxes, you should have these first 4 boxes filled in. Who does not have those first 4 boxes filled in? Is good? All right, now I'm ready for trees. Trees. So I'm gonna clear out my data. Second exit stat, yes. Second stat, 1 variable. Okay, hit data, X1. My first tree is 401 centimeters. Scroll down, scroll down. My second tree, scroll down, scroll down. Third tree, scroll down, scroll down. Fourth tree, scroll down, scroll down. Fifth tree. Okay, so now I got my 5 trees punched in. You guys got your 5 trees punched in? Then hit stat var. And yep, I definitely have 5 trees, and that's 5. Okay, scroll to the right. My average tree height is this many centimeters. That's my average tree height. Scroll to the right one more. And the sample standard deviation is this many centimeters. Again, think about like a plus or minus factor. Think about 2/3 of all trees will be within this many centimeters of this average. Okay. You guys good there? Okay. Who's got a question? Who's got a question? All right. All right. So I think everybody's good. Take us what you guys know I recorded yesterday's, and I'm also recording this one right now. So I'll load this classroom. If you missed a detail somewhere, then we'll be able to catch it. Okay. All right, now, while you guys are finishing that data, let me point out something about these numbers, right, and how they line up with these graphs, these curves. Right? You guys see it? Look at these mean averages: 101, 174, 408, 400. Right? Now everybody has different numbers, but see how dogs to people to trees is getting taller, taller, taller. Ah, that's why dogs, people, trees curves go left to right. Right? And also look at standard deviations: 16, 8, and 4. Remember, that's like a plus or minus factor. So the dogs is like plus or minus 16 centimeters, people's like plus or minus 8, trees like plus or minus 4. That's why the dogs have a really wide curve, the people's in the middle, and the trees is really skinny curve. You see that? Okay, all right. You guys ready for the next concept? Okay. All right. Z equals X minus mu over sigma. Z-score represents the number of standard deviations from the mean for a particular sample and is calculated with, okay, this is the formula. Determine the Z-score for each of the following. I gave you guys 2 dogs, 2 people, and 2 trees. Okay. Let me bring up this page of notes. All right, so we give you guys a big picture of what this means so that you aren't just like plugging away with numbers here. You say, okay, I can kind of see where this is going, what this means. Okay. Z-score. You're going to start with a particular sample, like a particular dog, a particular person, particular tree. Okay. Subtract the mean height, for the entire population, right? And that will tell you, do you guys see if you're above average height, that'll come out to positive, and if you're below average height, that'll come out to negative, right? I see it. It might be a small negative number, a small positive number, or a large negative or a large positive number, right? But what does it mean by large or small? Well, that's where you're going to divide by standard deviation. When you divide by standard deviations, that effectively tells you a count of how many standard deviations above or below the mean of particular cases. Hey, guys, that? Hey, because if you were, for example, exactly 1 standard deviation above the mean, you take the difference, you get, for example, like 16.3 and divide by 16.3, that will come out to exactly 1.0. So the Z-score is a count of how many standard deviations from the mean for a particular case, right? Right. Let's run some numbers. I'll run my numbers, you guys run your numbers, and we'll see what we get here. So we're doing time, we got short day going. Yeah, 4, all right. Okay, so my first dog, I'll go Z-score. I'm about to do 6 calculations on this paper. I got 68 centimeters for my first dog. Now, average dog height was this number. Okay. And standard deviation was this number. Oh, I'm so sorry, guys. I meant to mention one more detail. Okay. You'll see different notation. So X minus mu over sigma. You might also see this X minus X bar over S. Right, so mu could be the mean. X bar is also a mean. It's the same thing. And sigma or S, we're going to treat the standard deviation. Now, if you take a stats class, there's technically some little differences, and I'm glossing over that. But for our purposes today, you might see either of these notations, and we're just going to treat it as all the same thing. Okay. All right. So how many standard deviations? I do see I have a short dog here. This dog is shorter than average. How much shorter than average? I'm about to find out. All right, so I'm getting negative 2.02. Ooh, so this dog is actually a pretty short dog. He's 2 standard deviations below the mean. So I've got a Z-score of -2 for that dog. Right? I'm gonna try my other dog. Who's exactly 101 centimeters. Ooh, 101. It's not like an exactly average size dog, at least with my numbers. Okay. So I don't even need to calculate for this. Is it going to be 0 over anything? It's just a Z-score of 0, right? So that's that one right there. Right. If you have a Z-score of 0, that means you are exactly average on that particular metric. I have an exactly average height dog. Right, guys, yeah? Okay. Right, next one, a human of height, so many centimeters. So this many centimeter tall human. What's my average human height? Was this right here? Okay, so I do see I have a short human, like a below average height human. Right. How short? Well, here's a standard deviation. That'll give me that insight as to how short this guy is. Let's do. All right, I'm looking at maybe 1.4. Yeah, that's a pretty short human. So negative 1.7 for the Z-score. As we do more and more of these over the next few days, you'll see more and more context with that Z-score. Yeah, like 2 standard deviations below the mean, that's pretty far into the tail. These are like shorter than like 90-something% of everyone else in your group. But we'll get to that. We're working towards it. Okay. My other human is 190 centimeters. Okay, so this person's taller than average. That means he's going to have a positive Z-score. But how large is that Z-score? Well, let's divide by the standard deviation, the Z-score for this guy. Okay. 1.99. All right. Okay, so that's like 2 standard deviations above the mean, which is a pretty tall person. This person would be taller than like 90-something% of all people. It comes out to like, think about that. It's like taller than 95 or 97% people. Okay. Okay, and then trees. I have a tree that's 400 centimeters. My average tree height was 408.8. Okay, so I have a below average tree, below average height tree. Okay. Now, at a glance, we say, well, it's only 8 or 9 centimeters below average. Is that really crazy short? Well, if you had like a warehouse full of 1,000 trees, would this be one of the shortest trees, or would it be kind of a little bit below average? Well, again, that depends on the standard deviation. In this case, the standard deviation is this number. This will tell us how short this tree is compared to all the other trees in the group. Looking at negative 1.96. Ooh, yeah, that's a pretty short tree. That's like 2 standard deviations below the mean. I got one more to go. I got a tree of 425 centimeters. Run this. 425. 8.6 something. Whew. All right. All right. So now I got my 6 Z-scores: 2 dogs, 2 people, 2 trees. Again, everybody's numbers and scenarios are a little bit different, but I try to do like one below average and one above average, right? Or in the case of one of my dogs, it's exactly average. So you might get something like that. Okay. Right. You guys get is that working out for you guys? All right, everybody right? All good? All right. So here's what we do next. Guys, flip to Stats Puzzle B. That's the next page, right? Stats Puzzle B. Right. And yeah, let's just do a little bit more here. Right. So you guys see this bell curve going on right here? Okay. Now there's something in statistics called the 68, 95, 99.7 rule. Right. And what that means is that, oh, here. Do you guys see how there's there's some Z-scores written down below the bell curve? So a Z-score is 0, that's exactly average, right? Oh, look, mu, that's exactly average. Okay. If you're 1 standard deviation above average, that's right here. Then 2 standard deviations above, 3 standard deviations above, and then up to 3 below. You guys see it like plus or minus 3 standard deviations covers almost the entire population.
Yeah.
Right. Like if this is a population of like 1 million trees, for example, 1 million trees, you might have a couple of trees on this end and a couple of trees on this end, but that'd be like almost all the trees right there, right? Right. Okay, so here's how it goes. Within 1 standard deviation, plus or minus 1, that's 68% of all data. That's about 2/3, right? Right. Plus or minus 2 standard deviations from the mean, that covers 95% of all the data. And plus or minus 3 standard deviations from the mean covers 99.7% of all the data. So if you are beyond 3 standard deviations in either direction, you are an extreme for that particular metric. And we're using height as a metric for the example so far. You'd be extremely tall or extremely short if you're beyond, right? You guys see that? Right. Right. So we got here, got the formula for mean, formula for standard deviation, formula for Z-score. Okay, so we've done all this already. Right. Let's just do this this last example today, and then we'll call it a day. We'll just do this one right here. The volume of bottles for 1 liter bottles. Right. So I'm going to attach a story to this too. Let's say there's some factory that's filling up bottles, and the advertised volume is 1 liter. We got 1 liter bottles. But you think that machine that's filling bottles, like, do you think there's a little bit of a plus or minus factor because it's a machine? Sometimes a little bit more, sometimes a little bit less. Okay. Now, let's say you're a government official, and maybe you want to, maybe you're part of a consumer protection agency, and you want to see, is there truth in advertising? They're advertising 1 liter. Is it really 1 liter? And you have a government standard. And maybe your standard is something along the lines of, well, as long as like more than 95% of the bottles are as advertised, then you're okay. And maybe there's a couple bottles that's a little bit less, but we'll let them slide or something. Some standard, right? Okay, so you go grab 6 bottles off the shelf. You guys see 6 bottles right here? And we're about to crunch some stats and see if this is all right. We're gonna find out. Right, so do second exit stat to clear out your data. Yes, exit stat. Second stat, one variable. Okay, guys good so far? Okay. All right, then hit data. You should see X1. Right? Punch in your, time out real fast. I did something a little bit weird here. You guys see how I listed all the bottles in liters, but the boxes down here are in milliliters? Can you guys multiply by 1,000? Is that okay? So 0.99 liters, should I actually call that 990 milliliters, right? Is that true? Got a little unit conversion right here at the tail end of the school year. 1 liter exactly, let's call that 1,000 liters, or milliliters. 1,000 milliliters. 1,020 milliliters. 1,030 milliliters. And 1,040 milliliters. Okay. Right. So you guys multiplied each of those numbers by 1,000 to go from liters to milliliters, and then punch in those 6. You should have 6 numbers, right? Okay. Yeah.
Does it matter if you do the conversion after?
Yeah, you can do it after the fact. That's fine. Okay. Okay. All right. So then go to StatVar. Okay. Yep, I got 6 bottles that I grabbed off the shelf. Okay. X bar, the average average volume. I'm looking at this many milliliters average. Okay. And the one after that, standard deviation. That's like a plus or minus factor. I'm looking at this number right here, plus or minus that. Okay. Okay. And if you did everything in liters, you just multiply each of those numbers by 1,000, right? And your number should look kind of similar to mine, right? Kind of similar. Right. And so here's what I can say. If I grabbed a bottle at random, let's say there's like thousands of bottles on the shelf, right? If I grabbed a bottle at random, the average size is going to be 1,013 milliliters, and then plus or minus about 20 milliliters, 19 or 20 milliliters, plus or minus that should cover about 2/3 of all the bottles, right? I have a few bottles that are more than 20 milliliters, higher than this average, and some that are less than that, but yeah, plus or minus about 20 milliliters should cover about 2/3 of all the bottles. Okay, that's good. Now, let's say that we're going to grab a 7th bottle. So go back to the store, grab one more bottle, and it's got this many milliliters of liquid in it. So I wonder how short this bottle is, right? I do have one cell on the small side, so I should have a negative z-score. All right, let's run the z-score for this guy. You guys remember z-score goes the sample minus the average, all compared to the standard deviation. Guys remember that? Okay. So let's try it out. So I've got this many milliliters. I'm going to subtract off the average milliliters and divide by standard deviation milliliters. Okay. Milliliters. All right. Let's see what this z-score comes out to. It's a negative number. Of course it should be because it's less than average. Okay. Oh no, we're good. We got a long period here. So I'll just wrap this up. Right. Guys, we're still here for another half hour. Okay. All right, and then here's the last thing we'll do today is once you got your z-score, guys, is your z-score coming out very close to an integer value? Like mine's basically -1, right? Okay. It should come out to, is anybody not getting something very close to an integer? Right? Okay, well, let's just round this to the nearest integer. So I'll call mine -1, right? And then you can use this to answer this last question. What percentage of bottles contain less liquid than this bottle? So let's go back up to this bell curve. Now z-score -1, that would put me exactly right here, right? So less than that, wouldn't that be all that tail right there? Right? Let me see what that would be. Well, I gotta figure that out. I could here, I'll do this 2 different ways. I can add these up, 0.15 plus 2.35 plus 13.5. Right? Get that way. Right. Alternatively, I could say 50% minus 34. Right? 50% minus 34%. Either way, I'm getting the same thing. I'm getting 16%. Right. So if you also have a z-score of -1, like I do, then that means that only 16% of bottles would have less liquid than that. If your z-score is exactly 0, this number would be 50%. What about if your z-score is +1? Should it be, say 16% plus this middle 68%? Right? All right, guys, if your z-score is +1, this should be 84%. Okay? Right, who has a z-score they want me to run for them? Yeah, what's your z? Yeah, what? You have +3? Ooh, all right. If you have a z-score +3, that means that, so 100% minus 0.15%. That means that 99.85% of bottles have less liquid than that. So you won the lottery. You have a lot of liquid in your bottle. Z-score 1? Yeah, if you have z-score 1, I'm gonna do this 50% plus this 34%. So this 50%, right? Plus this slice right here, 34%, that brings you up to z-score 1. Right? It'd be 84%, right? Okay, guys, all right? No. All right. Well, so my classes don't get crazy off track. Call that a pause point right there. But if you have any questions, let me know. I can help you out.